Module 6, question 1, allows you to explore the effects of mutations in the DNA level and see what the effects are in the amino acid sequence of proteins. Recall that any mutation is always going to be at the DNA level, and those are permanent mutations. Changes in the tRNA, changes in the mRNA, changes in the protein sequence, those are going to be temporary unless it happens at the DNA level. So you're given a fictional or an mRNA strand, and in this case I'm going to make my own. So here we have AUG, U, C, U, U, A, U, C, 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 G, C, U, U, G, A. Oh, let's run out of space. Okay, and then the corresponding amino acid sequence from this will be methionine, serine, tyrosine, proline, alanine, and stop. Alright, so actually usually we don't write stop. We'll just leave it at that. So we have our 5 amino acid protein. Okay, check this, make sure that it's right. And sometimes it helps to maybe draw in lines separating the codons, because you can then see the triplets that that code for the amino acids. Okay, so now you're asked to diagram what happens to various mutations. So, you're supposed to fill in the coding and non-coding strands. So last week I made a mistake. I called the coding strand the template strand. Well, the template strand is a strand of DNA that's used to make the mRNA. So in this case it'll be opposite, right? It'll be a T over here, an A over there, a C, whereas the coding strand is the non-template strand. So in this case it'll look just like the mRNA. So recall that the mRNA strand looks just like the non-template strand or the coding strand. So the way I remember it is the coding strand is where you can see the codons. And often by convention we write the coding strand of the DNA or the non-template strand, because this way we can see the direct amino acid codons in the DNA without having to make it an mRNA first. Okay, so this is our coding strand. So I'm only going to write our coding strand. Again, our non-template will be the opposite. And then now you can see the codons in the DNA leading to the various amino acids. Okay? Alright, so the next thing you're asked to do is make mutations. Right, so the first mutation is going to be a deletion mutation. And again, mutations happen at the DNA level. So we're going to delete an amino acid, and we're going to delete that one right there. Okay? So now my resulting coding strand will be like this. ATG. That hasn't changed. TCT. Same with that. And then we have T. We have a deletion there. So then it goes TTC and CCG. CTT and GA. Now note what's happened. Our reading frame has changed. Right? So we have our first two amino acids are going to be the same, still methionine and still serine. But because we have this deletion, now our whole reading frame has changed from a TAT to a TTC. So now this is a phenylalanine, CCG is a proline, CTT is a leucine, and then this will be whatever else. So this protein is going to keep going. So not only have we changed amino acids downstream or after the deletion, but we've also made this protein carry on. So this protein is actually going to code for more amino acids. And insertion works similar in the sense that we're going to change reading frames. Okay, so now rather than let me erase this. So rather than now deleting, so we'll put this A back. Now rather than deleting, we can insert, let's see, maybe put an A right in there. Okay, so then our resulting mRNA strand would be ATG, TCA. So again, now we've shifted everything down, right? So now we made a TCA, and then this will be a TTA, TCC, CGC, TTG, etc., etc. So again, this is still a methionine, but this TCA now is a serine. Oops, that hasn't changed. And then leucine, so we've seen change. So, and again, anything after the insertion will be changed, and in this case, again, our protein is going to keep going. So things like insertions and deletions result in what we call frame shift mutations. And this is a change in the codon reading frame. And frame shift mutations are very powerful and I guess detrimental to the protein, because everything after the amino acid or after the nucleotide insertion or deletion will be changed because you're not changing the reading frame. Alright, so this is a different, or the effect of a frame shift mutation is much more severe than the effect of our next mutation we're going to look at, which is a base substitution. So a base substitution, like the name implies, is when we substitute a base. Okay, so now rather than having rather than an insertion or a deletion, what we're going to do is we're going to change a base. So let's see, let's take this CCC and we're going to change this C into a G. Okay, so now we've changed that. Everything still stays the same. Our reading frame hasn't changed. We still have methionine, serine, tyrosine, and then now this GCC codes for an arginine, an alanine, and then still our stop. So the only thing we've done in a base substitution is we've changed one amino acid. This is what's called a missense mutation, or a change in one amino acid due to a base substitution. If we were to, let's say, incorporate or have a substitution from this TCT to a TCA, this would now code for a stop. So now we have a truncated protein, just methionine and then stop. This is what's called a nonsense mutation, or a substitution that results in the introduction of a stop codon. And if you have a substitution, let's say this TAT to a TAA, that wouldn't change the amino acid, so that would be what's called a silent mutation. So a change in the base or nucleotide sequence, but no change in the protein. You should check that. I'm not even sure if that's correct. Okay, so that's the information you need. Again, do these problems with understanding. Don't do them for completion. Don't do them to just try to get the right answer. Make sure you try to understand these processes. See how whenever you change something in the base sequence has a resulting change in the amino acid sequence. Alrighty?